All right, so a couple of the problems on this worksheet deal with the Diels-Alder reaction. So I want to talk about those particular problems. In question number 2, it says, which of these structures would act as a diene for a Diels-Alder reaction? So we have to consider, what do we need in terms of a diene? Well, the diene portion that we're going to use has to be able to adopt this S-cis conformation where these two double bonds are on the same side. That's the only way that this Diels-Alder reaction is going to work. If we look at the structures that we have, 2 of these, A and C, actually have a diene. B and D do not have a diene. A has a ring system that has a diene that's locked into this S-cis conformation. C has a diene that's locked into an S-trans conformation. So C is not going to be able to react under these conditions. So we're going to want to react with compound A. So we try to predict the product of compound A with this maleic anhydride. We can see how we can put these molecules together. So let's take a look at these. So this is our structure for A, and we're going to react this with our maleic anhydride. Now I usually like to identify the carbons that are involved in my cyclohexene ring formations. We have 1, 2, 3, 4, 5, and then 6. We don't need to worry about regiochemistry in this case because we have a symmetrical dienophile. Anytime you have a symmetrical diene or a dienophile, the regiochemistry of the reaction doesn't matter. The stereochemistry is still going to be important. If we look at the diene that we have 2 carbons that are bridging the 2 ends of our diene system. So here we have a 2-carbon bridge. Anytime that we have some carbons that are bridging carbon 1 and carbon 4 of our diene, we're going to end up with a bicyclic system in the end. So for this particular reaction, this is the type of bicyclic system that we're going to have. And I'm going to go ahead and number my atoms around this ring so you can tell where they all come from. This is 1, 2, 3, and 4. So this is going to be carbon 5 and carbon 6 on the other end. Now, Diels-Alder reactions are always endoselective, which means that these carbonyls want to be on the same side of the diene when they react with one another. That makes those carbonyls end up in this endo position on our final product. So these H's are in the exo position. They're on the opposite side of where the alkene is at. These carbonyls are in the endo position. They're on the same side as our ring system as that double bond. It may be difficult to see in this particular case, but if we have a typical diene that reacts with the dienophile, that carbonyl points in the same direction as that diene does. So the H or whatever's on the other side points in the opposite direction. So the ring system in this case would be sticking like that, away from where this is at. And that's what we see, that ring, that bridge, is on the opposite side of where these carbonyls are at. Now we're not quite done with our system yet, because we have to attach on this other ring system here. And this is the one that causes the most problems when you look at this. So if this was carbon 1, we could say that this is carbon 0. So 4, 3, 2, 1, that makes this carbon 0. So we have a 6-membered ring that is appended on here. So if I have 1 carbon, 2, 3, 4, 5, 6. So this is that 6-carbon ring that's attached at that position. And we know that going from carbon 1 around the ring is where we hit the double bond. So the double bond would be added right there. Now the one thing we don't know in this picture is what the stereochemistry of that particular carbon is going to be. It is not denoted in our starting material here, so we do not know what that stereocenter is going to be there. Clearly, that is important if we're thinking about the stereochemistry of the overall product. But if it's not given, then we can't infer what that's going to be in our product. So that's one of our Diels-Alder questions. The second one asks us which of these compounds would react the fastest as a dienophile in a Diels-Alder reaction. So here we have a diene. Now, dienes typically have electron donating groups attached to them, like this carbon group here. A dienophile typically has some kind of an electron withdrawing group attached to it. So with that in mind, if we look at the potential compounds that we have, compound B is the only one that has an alkene that is attached to an electron withdrawing group, which is this carbonyl. So compound B must be the dienophile that we're using in question. So let's take a look at what happens as we take compound B and react it with this cyclopentadiene. So for this problem, we have cyclopentadiene, and we have compound B. Again, we have a symmetrical diene. If any of those partners are symmetrical, then we don't need to worry about the regiochemical outcome of this. We do need to worry about the stereochemical outcome. If we try to take a look at how these two things are going to come together, here's our diene with our bridge. And that's going to interact with the dienophile alkene. And now we want this carbonyl to be underneath where that diene is at. So we're going to draw that in this direction. So when this diene comes down on top of this, it's coming down on top of it with the carbonyl pointed in that direction. So if we translate that into the product, we can almost see that bicyclic system right here. So I can draw out that bicyclic system, put in my alkene, and now the carbonyl wants to be in that endo position. Put the carbonyl there, put the H here and the H here, and that's our product. So the carbonyl is on the opposite side of where that bridge is at. Here's the carbonyl, there's the bridge. We can almost generalize this information if we're trying to figure out what the stereochemistry of our products is going to be. Anytime that we have a diene and we have our groups that are pointing away from the diene, if you notice these things are pointing away from the inside of that diene, and we react this with a dienophile that has some kind of a carbonyl or electron withdrawing group, in the end, we are always going to see those R groups be on the same side as whatever your electron withdrawing group was. This is always going to happen. So we can use this kind of as a mnemonic to figure out what the stereochemistry is going to be in these cases. If we have a group that points towards the inside, like a bridge in this case, that's always going to be on the opposite side, or trans to where that carbonyl ended up. And we see that illustrated in this example. This carbonyl is on the opposite side of where this bridge is at. It was pointed to the inside. These H's are pointed on the outside. These H's are pointed on the same side of the ring as that carbonyl is going to be. So hopefully this information is useful as we try to solve some of these challenging Diels-Alder reactions.